You don't want to be like him, right? You clicked into the right video. Calculus has been a nightmare to students, especially STEM, and also high schoolers. You might have watched memes or rumors about how hard it is. But don't worry, we will make sure that calculus has never been easier. By the end of the video, you can call yourself a king of calculus. Welcome to Sorn 101.
First off, let's talk about functions. Have you guys ever heard of it? If not, let me tell you. So think of a machine. You put something into it and that machine did something to them and it came out as a new things. So things you put in are called inputs and what comes out are outputs. So in calculus, we have x as input and fx or y as output. And we can tell the operation inside the machine as a rule or an equation. For example, if we have the rule y equals 2x, think of it as a doubling machine. It doubles the number that goes into it. Like if we have input as 3, and the output will be 3 times 2, which is 6. So you might think that all equations are functions. Then the answer is no. To be a function, an equation must follow this key rule. Each input can give only one output. If a single input gives you more than one output, then it's not a function. For example, the circle with a radius of 5 equation is x squared plus y squared equals 25. So if we plug in x equals 0, then we have y as plus or minus 5. So one input gives me 2 outputs which don't follow the key rule I mentioned. So every circle is not a function. And there's also another way to check if it's a function. I would call it vertical line test. If you plot an equation as a graph and you draw a vertical line anywhere on it, if the line touches the graph 2 or more places, then that is not a function. So, this is what you need to know about functions before we start working with limits and derivatives. Of course, there's a lot more to functions in general, but for now, this is enough to move forward.
Now, let's discuss one of the most important ideas in calculus, limits. Imagine you are driving closer and closer to the stoplight, but you haven't actually reached it yet. That's like approaching a limit. For example, if you slow down as you approach the red light, your speed goes closer and closer to 0 km/h. So we can say the limit of your speed as you approach the stoplight is 0, even if you haven't completely stopped it yet. We can write it like limit of f of x as x approaches a equal to L. This means that as x gets closer to a, the value of f of x gets closer to L. For example, if f of x equal to 2x plus 3, then limit of 2x plus 3 as x approaches 1 equal to 2 times 1 plus 3 equal to 5. For most basic functions, we can just substitute the value directly, but not always. Sometimes, a function behaves differently from the left and from the right. That's why we define one-sided limit as left-hand limit, limit of f of x as x approaches a from the left, and right-hand limit, limit of f of x as x approaches a from the right. The limit of f of x as x approaches a is exists only if both sides are equal. Before we move on, let me quickly point out what vertical and horizontal asymptotes are. Let's start with vertical asymptote. Occur at value of x while the function is undefined and grows without bound. For example, in f of x equal to 1, over x minus 2. The function is undefined at x equal to 2. As x approaches 2 from the left, f of x will approaches negative infinity, and from the right, f of x will approaches infinity. So, x equal to 2 is a vertical asymptote. Horizontal asymptotes describe how a function behaves as x becomes very large or very negative. For example, f of x equal to 2x plus 1 over x plus 3. Levels of at y equal to 2 as x approaches at infinity or x approaches negative infinity. So, y equal to 2 is a horizontal asymptote. Now, let's connect these two limits. When a function grows larger and larger without bound, as x approaches a certain point, we say the limit is infinity. Imagine driving down a very steep hill. The closer you get to the edge, the faster your speed increases. For example, limit of 1 over x as x approaches 0 from the right equal to positive infinity. This is exactly what creates a vertical asymptote. On the other hand, we can ask what happens as x becomes very large. There is a limit at infinity. For example, limit of 2x plus 1 over x as x approaches infinity equal to 2. As x increases, the function approaches 2, which corresponds to a horizontal asymptote at y equal to 2. So, vertical asymptotes relate to limits where the function blows up near a specific x value, while horizontal asymptotes describe the long-term behavior of the function as x goes to infinity. Now that we understand what a limit is, let's learn how to work with them efficiently. When functions become more complicated, we can use a set of simple and powerful rules called the limit laws. 1. Sum law for limits. 2. Difference law for limits. For the sum and difference law, we can take the limit of each part separately and then add or subtract the results. 3. Constant multiple law for limits. If a function is multiplied by a constant, you can simply take that constant outside the limit. 4. Product law for limits. It is that if each function has its own limit, then the limit of their product is just the product of their limits. 5. Quotient law for limits. You can take the top and bottom limits separately, but be careful that division by 0 means the limit doesn't exist or go to infinity. 6. Power law for limits. And 7. Root law for limits. For power and root laws, in other words, taking powers or roots outside works naturally with limits as long as what's inside makes sense. Now we know how to handle limits algebraically. Next, we'll see how limits connect to continuity.
The next topic is continuity. In simple words, a function is continuous if its graph can be drawn without leaving your pen from the paper. There is no hole, no jump, and no break in the graph. Then, how can we prove that a function is continuous at a point? There is something called the three-step continuity. We can use the following three conditions to check if a function is continuous or not. The first step is that the function is defined at a. The second step is that the limit as x approaches a of fx exists. How can we show that this limit exists? You need to show that the limit as x approaches a from the left side is equal to the limit as x approaches a from the right side. This condition will show that the limit exists. The third step is that the limit as x approaches a of fx is equal to fa. So, that's a definition of a continuity at a point. If any of these fail, for example, the graph jumps or has a hole, then the function is discontinuous at a point. Let's go ahead with the first example. Let's check if fx equals x squared is continuous at x equal 2. We find f2 equal 4 and the limit of x squared at x approaches 2 is also 4. Since both values are equal, the function is continuous at x equal to. For the next example, let's look at this function. Fx equals x squared when x is not equal to 2 and fx equals 5 when x equals 2. I will give you around 20 seconds to find the answer to this example. Time's up. Here is the solution. We can observe that f2 equals 5, but the limit as x approaches 2 of x squared is 4. They are not equal, so the function is not continuous at x equals 2. Now, let's talk about indeterminate forms, another common challenge in limits. Sometimes, when we plug a number into a function, we get something like 0 over 0, infinity over infinity, etc. This is called an indeterminate form, meaning a value that we are unable to evaluate. It doesn't mean the limit doesn't exist, it just means we need to simplify first. What does simplify mean? Simplify is a verb that means to make something less complicated and therefore easier to do or understand. Then, how to solve it? We can use factorization, rationalization, or other methods to simplify this expression. What do factorization and rationalization mean? Factorization is a noun. That means the dividing of a number into factors. For example, x squared minus 4 can be factorized by x minus 2 times x plus 2. Another word, rationalization is a noun. That means removing a square root from the denominator of a fraction. For example, we have 1 over the square root of 2. To rationalize the denominator, we multiply both numerator and denominator by the square root of 2. Then we get the square root of 2 over 2. Now, let's continue with the first example. The limit as x approaches 1 of x squared minus 1 over x minus 1. You can directly substitute x equals 1 here, because it gives 0 over 0. So, we have to do something. The method we choose to do is factorization. We factor the numerator x squared minus 1 equal x minus 1 times x plus 1. Then, we cancel x minus 1 and we are left with the limit of x plus 1 as x approaches 1. Finally, we substitute 1. So, 1 plus 1 equals 2 and the answer is 2. Even if it looks impossible at first, by simplifying, we found the real limit value.
Derivatives. When we talk about derivatives, we're really just talking about one simple idea: change. To start measuring this, we need a simple tool, and that tool is slope. Imagine this straight line representing something that changes at a constant rate. If we pick any 2 points on the line, let's call them point A and point B. We can easily find the slope from those 2 points by using this formula. Slope equals change in y divided by change in x. This gives us the average rate of change between the 2 points. Since the line is straight, this rate is consistent everywhere. In calculus, the derivative is the instantaneous rate of change of a function. But what does instantaneous mean here? Instantaneous rate of change refers to the slope of the graph at one specific moment, or exactly 1 point. From the linear graph we looked at earlier, the derivative, or the instantaneous rate, is equal to the slope. But what if our graph isn't a straight line? What if it's a curve? where the steepness is constantly changing? Well, we can still find the slope using point A and point B, just like a straight line. The problem though is for each 2 points, the slope differs. The question is, if we want to find the slope at exactly one specific point on that curve, how do we do it? The question is, if we want to find the slope at exactly one specific point on that curve, how do we do it? Now, here's the tricky part. If you want the slope at just one point, let's say point P, the 2 points we use in the formula would actually be the same point. That means both the change in y and change in x are 0. So we would end up with 0 divided by 0, which that makes no sense in math. That means both the change in y and the change in x are 0. So we would end up with 0 divided by 0, which makes no sense. We are trying to measure a rate of change, but when we measure it at a single point, the change in y is 0 and the change in x is also 0. The answer collapses into 0 divided by 0. It's a paradox. How can we measure change when nothing is changing at the exact point? How did mathematicians find a way around this deadlock?
The smart idea they came up with was, instead of forcing the 2 points to be exactly the same, we make them closer and closer and closer. We still use the slope formula, but instead of having the same point twice, we move one point closer and closer to the main point. As we move point Q closer to point P, the line connecting them gradually rotates. Eventually, the line becomes one that just touches the curve at point P. At that one single location, we call this the tangent line. The slope of this tangent line is the instantaneous slope or the derivative we are looking for. The idea of letting delta x become so small that it approaches 0 is the core concept called the limit. This is a clever trick that allows us to calculate the true slope while avoiding the 0 over 0 problem. Now, let's translate this idea of change approaching 0 into a simple visualizable calculation. In calculus, when we talk about a change that is approaching 0, we use the symbol d instead of delta. dx means the tiny change in x, and dy means the resulting tiny change in y. The derivative, written as f prime x, is just a dy over dx. Let's see how this works for a concrete function fx equals x to the power of 2. Think of it like a square with side x. So, the area of a square is x to the power of 2. If we increase the side length just a tiny bit, let's say dx, the new area that is added comes from 3 sections. The new area added is made up of 2 rectangles, each x times dx, and one tiny square, with the area of dx to the power of 2. So, the total change is 2x times dx plus dx squared. And since dx is extremely small, approaching 0, we can simply ignore the dx term. It vanishes in comparison to 2x. Therefore, the derivative of x to the power of 2 is 2 times x. This is how the geometric change reveals the slope.
From that example, we can see a pattern. If you did the same for x cubed, you'd find the rule. The derivative of x to the power of n is n times x to the power of n minus 1. That's called the power rule. And this geometric way of thinking isn't just about polynomials. We can use the same visual logic with concepts like the unit circle to prove things like the derivative of sin x is cos x. This shows that calculus isn't just about memorizing formulas. It's about using geometry and visualization to deeply understand the most subtle changes in the world.
What เหี้ยเลยวะ